you. So, welcome everyone to this morning's E3SM All Hands webinar. I have the honor today of introducing Daniel McCoy, which is my pleasure to do because I've known Daniel for about 10 years now. We worked together pretty closely back then on a paper to understand the sources of variability in cloud drop number concentration over the Southern Ocean. And then our paths have kind of diverged. And now he is an assistant professor at the University of Wyoming and has an exciting new project there called Proceed, which is funded by the DOE EPSCoR program to help us on the E3SM project with using observational constraints, including from ARM data, to really better constrain and understand uncertainties in aerosol cloud interactions in E3SM. And I'm really excited to see what they're able to do on this project. And he's going to give a really interesting talk. I think work he's done already doing similar work for the CESM model. So with that, I'll hand it over to Daniel.
Oh, yeah, thanks so much. And yeah, it's good to be back and have our paths reconverge now that I'm in the US. Yeah, so I don't think I need to say too much more about this. We're hoping to look at sort of parameterized subgrid scale processes and models using a perturbed parameter ensemble with the goal of sort of setting up a framework where you can use the ARM observations to constrain a lot of these processes, specifically microscale processes. And we think that a perturbed parameter ensemble is a pretty good tool for this because a lot of the processes that end up driving sort of global scale phenomena like this, 1,000-kilometer wide extratropical storms are ultimately microscale processes. The hydrometeors and cloud droplets that make up those storms are microscale. So even as we move to progressively finer grid scales for our global models, it's really for the foreseeable future, we're parameterizing a lot of the relevant cloud aerosol processes. And looking across at least the last few generations of climate model, a lot of the leading terms in terms of feedback and forcing uncertainty are pretty dependent on microscale processes. On the left is a plot from Mark Zelenka's 2020 paper showing that most of the uncertainty in the feedback is ultimately due to boundary layer cloud. And the figure on the right is from Duncan Watson-Paris's recent Nature Climate Change paper, just illustrating that what we believe about the historical aerosol cooling ultimately has a lot of leverage in terms of what 21st century warming looks like. So while I imagine this is really old hat to most of the people on this call, perturbed parameter ensemble is a way to explore parametric uncertainty in a model, in this case in ESM. And parameterization is just the process of abstracting some sort of subgrid scale process to an equation. So I have this flowchart I borrowed from Andrew Gettleman, actually, just illustrating linkages between different cloud and precipitation processes. And each one of those lines has a separate, parameterization you have to develop to represent it in the model. And I'm going to pick on auto conversion for the rest of the talk. So we can abstract that to power law that is just telling about how much liquid cloud there is, the QC term, and how many cloud droplets are the ND term. And this tells you about the loss rate of cloud to rain. So there's a couple of choices that are made here. One is that we're actually going to treat this process. Two is that we're going to treat it as a power law. And then we have to choose parameter values, A, B, and C terms. We can imagine a perturbed parameter ensemble, just the simplest one we could possibly imagine. Maybe we're just looking at auto conversion and we can sweep through the B and C coefficients there and explore how those affect some sort of macro scale observable like the global mean cloud fraction. And at least in my mind, there's kind of two main reasons to use the PPE. One is performance in your model, and the other is process insight, understanding how subgrid processes project onto the global mean. our global behaviors. A caveat to this is just parameterized processes, so structural error from untreated or untreatable processes isn't really addressed here. I don't have time to discuss this, but there are ways to try to suss out using PP whether there is structural error. So briefly, performance is pretty simple. It's that if you want to tune your model to look a lot like observations, you can do that pretty efficiently with a PPE. You can imagine our same super simple PPE with just two parameters. We might sweep those parameters and find a minima in RMSE versus some set of observations we think are worthwhile to match. And if we match, the one thing about this is that it gives us kind of an objective idea of how much uncertainty there are in things like the climate sensitivity or other response terms, because these things tend to be quite nonlinear. And so the minima in RMSE might map to quite different climate sensitivities, for instance. Similarly, process insight is one of the applications of this, where a nice example of this is that we still need models to look at causal processes, but PPEs give us a useful way of mapping how those processes are important. And so this is a paper from Ken Carsla's 2013, or a figure from Ken Carsla's 2013 paper, showing that essentially natural processes, biogenic emissions, and other natural sea spray are driving most of the uncertainty in aerosol cloud interaction cooling, even though the term we're looking at is driven by anthropogenic change. So our project, as Susanna said, is we called it PROCEED, which stands for Perturbed Physics Ensemble Regression Optimization Center for ESM Evaluation Development, which I realize there's an acronym within the acronym, but we're pretty proud of getting something that spelled out something. It's a 2-year project, started in fall 2023. We've been able to hire on postdocs that started in February of this year. It says it's EPSCoR funded. The relevant universities are University of Wyoming and University of Hawaii at Manoa. And then we're being collaborated with on the proposal by Pacific Northwest National Lab and Lawrence Livermore National Lab. Within this 2-year chunk, our project goals are to build an adaptable PP framework in ETSM v3 using Latin hypercube. And the idea here is to make a code package that we're looking at one science problem, but perhaps you're interested in, I don't know, the methane cycle. And the idea is to give you a code package that you can apply without reinventing the wheel. I should note here that within this project, we're looking at just the atmosphere model, because it's really, really hard to couple a PPE for semi-obvious reasons. One of the central goals of PROCEED is not only developing the software package, but also thinking about ways that we can use ARM observations, which we believe are really apropos for the problems we're interested in, to constrain what's a relatively coarse grid scale. And so understanding sampling and representativeness uncertainty. The science goal within this 2-year chunk is to constrain the aerosol cooling, the cooling due to aerosol cloud interactions using observations from ENA. This is an artist representation of that from the proposal. So we've been lucky to be able to hire on several excellent postdocs who are interested in this problem, Jacqueline, Travis, and Hunter. And we have a fairly interdisciplinary faculty team at EPSCoR supported universities on the right. So if you see us at conferences, you can say hi. I'd like to specifically acknowledge support from my grad students who are supported on PROCEED, but did a lot of the work developing the ideas that went into the proposal. And they have other sources of funding that they're working on right now. But briefly, I thought I'd outline kind of the flow chart of how we're envisioning this project coming to fruition. So this is stuff that Jacqueline's been doing in her first month and a bit here. And she's been working a lot with Andrew Kirby, who's a research faculty within our School of Computing. The idea here is that we are going to sample a bunch of parameters across what we believe are plausible ranges. So we just use Latin hypercube. It's just a Python script to generate a set of n ensemble members sampling over p parameters. And We unite this with currently E3SM v2, which is what we've got working on Derecho, which is the N-car computer. We have 80 million core hours a year to do this. So we're using the computer that we have an allocation on because it's based in Wyoming. And we're using this slick software package developed by Sandia called Dakota, where Dakota efficiently takes the parameter values from the Latin hypercube and combines it with the base case for E3SM, and then generates the PPE members that we then submit onto Derecho. So this is just the PPE framework, and it's actually worked out pretty well. And Jacqueline and Andrew have done a nice job setting this up. And the end goal here is that we're going to take our set of observations that come out of the PPE, or a set of model output that comes out of the PPE, and throw out implausible parameter configurations using observations. And the hope here is that once we do that, the emergent behavior of the model, for instance, the forcing in this case, and I've just stolen this figure from Jill Johnson, is constrained by what we can actually observe in the current climate. And one of the big challenges of Proceed is getting the observations from ARM to be kind of interoperable with the E3SM output. And this is something that people have done a lot of work on, and so we're leveraging existing work within the field. For instance, instrument simulators. So we're hoping to use the EMC squared simulator that Israel Silber has developed. And this is a really cool package because it lets you look at what the radar reflectivity would be coming out of your global model and compare it kind of apples to apples with what's coming out of ARM. And there's actually a lot of good reasons to want to use the raw observational output rather than sort of state variables like precipitation rate or cloud mass. We're also interested in understanding the impacts of spatial sampling differences between E3SM and the observations. So this is a figure from Adam Varpel's recent paper, illustrating that there's actually pretty good agreement between the satellite footprint and ARM, but at the same time, there's quite a bit of heterogeneity within the grid cell surrounding, for instance, in this case, ENA. And so what we're going to be doing is leveraging output from the large eddy simulation lasso effort to evaluate this spatial heterogeneity and get an idea of sort of what the observational constraint tolerance on the relatively coarse grid is. And finally, we're using Latin hypercube. As you might have noticed, we're not uniformly sampling in each parameter dimension. And the reason for this is we want to look at a bunch of parameters, but if you uniformly sample in each parameter dimension, it gets really, really expensive. So if you have p parameters and you're sampling n points in each parameter, that's n to the p ensemble members, which is still really expensive. So we're going to use, in this case, essentially machine learning emulators to fill in the space around random samples that simultaneously sample in every parameter dimension. One dimensional illustration is given from Lindsay Lee's kind of seminal paper on this on the right, showing Gaussian process, which is what we're intending to use. But we'll be using the Earth System emulator package that Duncan Watson Paris's group has put together that allows you to rapidly easily switch between different machine learning approaches. So that's kind of the top level flow chart of this, where we have the observations and the PP on the left, and a big portion of Proceed is finding ways to unify those through emulators and simulators and sampling uncertainty. And then once we can throw out implausible parts of the model space, we're hoping to have some insight into both climate prediction and what are the important processes that drive variability. So as Susanna mentioned, I'm showing some preliminary results that we've done on our path to developing this proposal using the CAM6 PPE. And we did get the pre-alpha build of the E3SM PPE running, I think, last night, but obviously we don't have any analysis for it yet. The CAM6 PPE is described, and Andrew described this last year. And you can watch that there. Briefly, if you don't remember, it's sort of the same setup. It's 45 parameters randomly sampled. There is pre-industrial present day and plus 4K simulations. what we're looking at is the pre-industrial present day difference to get an estimate of aerosol forcing. There's a preprint describing this by Trude Eidhammer if you want to read this. So the problem that I'll be discussing today is aerosol cloud adjustment. And I think this is probably familiar to quite a few people on the call, but briefly, as you go from the pre-industrial state to the present day state, you add pollution that gives you additional sites to nucleate cloud droplets on. This is illustrated in the bottom left here in Ken Carr's last book chapter. That increase in the number of droplets increases the scattering cross-section of clouds and makes them brighter if you hold the amount of liquid in the clouds constant. But as you change the number of cloud droplets, it changes processes in the cloud and potentially change macroscale things like the coverage and thickness and height and so on. The two main processes that we think are driving aerosol cloud adjustments in the field, and these are supported by observations, are precipitation suppression. So as you increase ND, that makes it harder for precipitation to form. It increases the liquid water path of the clouds, so the integrated mass of liquid to the top of the atmosphere, and that cools the climate. On the other hand, size-dependent entrainment tends to thin cloud because the entrainment is enhanced as you increase cloud droplet number concentration, and that decrease in the cloud liquid mass leads to warming. So there's this bifurcation and effects. It's kind of that leads to a lot of uncertainty in the overall forcing. And typically precipitation, well, almost always precipitation suppression is parameterized specifically by that autoconversion parameterization I was picking on at the start of the talk. Size-dependent entrainment is very rarely parameterized. However, if you look at the observations, there's this negative correlation between liquid water path and ND that appears in the satellite record very prominently. And so sort of natural question is this indicates that size-dependent entrainment is maybe important, but it's not parameterized in models, so there's a huge bias in our models. If you look at sort of recent ESMs, and this is from Johannes Molmestadt's current paper, there's a negative correlation that appears between liquid water path and ND, even though size-dependent entrainment isn't explicitly parameterized. So a natural question is this good if we somehow, what is driving this behavior, and can we have agreement with the observations? So this is work that actually my student August Mikkelsen presented last week for his master's defense. So it's pretty pretty fresh off the presses, but one of the things that was pointed out in Ed Griesberg's original paper pointing out this negative correlation is there's a lot of confounders in the relationship linking microscale and macroscale cloud behavior. This is illustrated here where we can look at cloud droplet number concentration, the cloud liquid water path, the precipitation rate, and the linkages between these, and they're driving by our large scale environment. And the thing we're specifically interested in is that arrow that goes between aerosol cloud adjustments and cloud liquid water. That's or between cloud droplet number concentration and cloud liquid water. And that's the adjustment term we're interested in constraining, but simultaneously precipitation formation is driven by cloud liquid water, and that leads to both coalescence and impaction scavenging. And so this isn't a causally distinct system that we're looking at in the present day. And in addition to these internal correlations, we also have air mass history driving what's ultimately dry polluted air, so driving all these. So I would argue that ARM observations are kind of uniquely well situated to answer some of the questions surrounding aerosol cloud adjustments. So what August did for his master's is he looked at liquid water path from the microwave radiometers at ENA, precipitation rate from the disdrometer, and cloud droplet number concentration from the end drop product. And using these, you can kind of get an idea of all these parts of this causally ambiguous system. But even though you have an idea of all these state variables, you're still in correlation world rather than causation world. So August went through and looked at the mean state of all these variables and their correlations. And this is from the observations, so this isn't the model yet. And the correlations between precipitation, ND, and the amount of the liquid water path kind of match our a priori expectations based on cloud physics. But the neat thing that you can do here is that you can perform the same analysis in the CAM6 PP. And this is kind of big nasty plot where you just go through and take all these things that you can actually observe and you correlate them across the 260 PPE members with the parameter values. And what I'd like to point out is that there's actually these kind of strong bands of correlation where specific parameters that are telling you about subgrid scale processes are lighting up. And so we can zoom in specifically on the auto conversion parameters here and see that these things that we kind of suspect are important to the auto conversion are actually telling us about are linked to the observations we can make. So I won't go into the details, but these actually make a fair amount of sense based on what we expect a priori. So the natural thing to do is say, well, within its structure, can CAM6 actually reproduce the observations? And it turns out it can. So on the left side, in all these plots we have, the gray distribution is the prior from the PPE, and the colors are the constraint from the observations. And what I'd like to point out here is it's not really all that important whether the observations are in the middle of the PPE, it's just whether it's somewhere in the PPE. The mean of the PPE is sort of a construct based on expert elicited parameter ranges. And generally, the observations do fall pretty well within the ability of the PPE to match them. Caveat to that is this liquid water path to ND correlation term that we think is telling us a lot about adjustments. And arguably, it's kind of on the edge of the PPE. I would say this is partially based on decisions we made about parameter ranges, but it is within the range. So the CAM6 model is actually totally capable of gaining negative correlation, even though it doesn't have parameterized entrainment. And you can just look at the raw ensemble members coming out of the CAM6 PP to try to start to get an idea of what's going on. So these are varying a bunch of stuff simultaneously, but we can just look at the dependence on two parameters here. So this noise is kind of artificial from like the convection parameterization being varied as well. On the left is the dependence of that regression on the ND exponent in the autoconversion that drives precipitation suppression. And as you go to the left, precipitation suppression gets stronger. The slope of that regression gets more and more positive, like we'd expect. But also, we can see that the liquid water path PI to PD difference gets stronger and stronger. So precipitation suppression and adjustments are growing. However, if we look on the right side here, this is the accretion enhancement factor. It's just really driving coalescent scavenging in the model. And what you can see is as accretion gets stronger, the slope of that regression gets progressively weaker. So you can imagine sort of a balancing act between precipitation suppression and accretion that leads to this overall observational behavior. But the delta liquid water path between PI and PD doesn't really depend on accretion, but it does depend on that precipitation suppression. And so what we're seeing from the observations in the present day, you have to kind of interpret it relative to these behaviors. One interesting thing is that if you go through and you constrain delta liquid water path between PI and PD from CAM6, using the observations, you still get an overall positive delta liquid water path. And arguably this constraint's not great because the emulator could be a little better, but working on that for the paper. The point I'd like to make is that even when you constrain to all these pretty negative or near zero slopes for liquid water path versus ND, you kind of constrain to the CSEM2 default, which is inherently kind of interesting because what we'd expected just based on sort of model democracy is if you look at the aerosol cooling term across CMIP6, CSEM2 is actually an outlier from the models, but at least within what we've been able to do here, it's pretty consistent with ARM. So this isn't to say that entrainment, size-dependent entrainment is not important or anything like that. It's just saying that we can match the observations pretty well without invoking it. And so we need to think about cases where we could maybe outline some structural disagreement between the observations and the models beyond this regression slope. So anyway, I'm actually kind of ahead of time. To summarize, I think these preliminary results in CAM6 illustrate the utility of the ARM observations to answer some of these questions about aerosol cooling. coupled with a PPE where you can actually figure out what the processes are that are at work and provide some constraint. Um, we're really excited to apply this to E3SM in the next month or two. Um, so we already have a pre-alpha build in E3SM v2, and we're working on v3. We have a GitHub web page. It's a stub right now, but you can check back in throughout the project. We're really excited to hear from you and whether you'd be interested to collaborate. Specifically in the science stuff I presented, Johannes Malmstedt's presenting some of this in August. Last thing I'll say is we have a relevant climber workshop, if this seemed interesting to you. It's being held in Wyoming at the end of October. And hope maybe see some of you there. So thanks.
All right, great. Thank you.